Okay.
Good evening, all people participating, ladies and gentlemen. So this is the fourth lecture in the webinar organized by the Belgian Physical Society, the webinar on nuclear fusion. In this talk, we focus now on materials research for fusion. It means what can we do in practical experiments to find out what is the best first wall for a fusion machine. You remember that the wall will be bombarded by neutrons and all kinds of other particles. They can cause damage. And what is the best wall? How to find out, and what is the device to use? This all and more things will be explained by Juan Kastner, who is from the Fusion for Energy organization and working at ITER, and has been a key person in his period in Japan to develop the source to full maturity. So, Juan, I give the floor to you.
Thank you, Jeff. Good afternoon, everybody, or good evening. I'm sorry for the late start of this talk, different to the typical time as 4 o'clock, but I have some commitments here in Cadarache that didn't let me do it at 4. So I will try to explain you where we are with one of the milestones, essential milestones in the fusion program, which is the availability of a fusion relevant neutron source. Okay. So I'm starting in a very funny way, if you want, with a document that was prepared in '53 by an American military, which was the program leader of the first nuclear reactor aircraft. Was not aircraft, sorry, ship aircraft carrier, which was in the '53. It was the first, of course, the nuclear reactor was at first a military application. And once he managed to succeed, to make the project successful and make the motor work, he wrote a memo to the Congress in which he declared what we consider had been the pressure and unnecessary pressure that he had been experienced. And this little memo, which he called paper reactors, real reactors. I would like to highlight some points because I think that they are very actual, even if more than 50 years have passed since. He devotes some words to the policymakers. He says, these people are no less interested in what a reactor plant will do, how much it will cost, how long it will take to build, and how long and how well it will operate. He also explains what an academic versus a practical reactor is. I believe that this confusion stems from a failure to distinguish between the academic and the practical reactors. And he identifies the main characteristics, the main features of an academic reactor. He says it is simple, it is small, it is cheap, it is light, it can be built very quickly, it is very flexible, it's in purpose, very little development is required, it will use most of the shelf components, and the reactor is in the study phase. It's not going to be built immediately. So, I mean, this is the scenario of the 50s, the first program leader of a nuclear reactor, the first nuclear reactor, successful nuclear reactor. But why am I talking about this in this introduction, in the introduction of this talk? I would like to stress that fusion program, you will see why. I mean, fusion program demands 2 simultaneous milestones. One is indeed the success of ITER, and another milestone, which is today is overlooked, has been overlooked for years because of the difficulties to make ITER take the dynamic that is taking now towards success. And the second milestone is the availability of 14.1 MeV neutrons with sufficient flux to reach suitable DPAs in a timely manner. You've heard and you will keep on hearing in the future about magical solutions for fusion reactors that supposedly makes a future a waste of resources. Indeed, ITER is expensive, ITER is huge, and ITER is demanding a huge amount of resources. But the answer to this is very simple. And the development of superconducting materials allow conceiving more compact tokamaks with higher current fields in smaller volumes. This is clear. ITER, in fact, is at the edge of what the superconductor that it's using can provide. We are using nion-13 in the TF coils and in the central solenoid, and neon tie in the PF coils and the correction coils. In the TF coils with 11.8 Tesla and 68 kiloamps, it's at the threshold of with very little margin of temperatures for the superconducting state. And in the central solenoid with a little higher current and little smaller current and little higher field, we are basically in the same scenario. It's very little margin in temperature for the superconductor to operate. With the high temperature superconductor that we have nowadays, we have more margin, so we can input higher current, so we can put things in a more compact manner. However, essential aspects of the degradation of materials and nuclear safety aspects are completely ignored in this proposal of projects. Let's see, let's pass. The need of fusion material testing is known for long, and in fact, the US led the research on its origins. Counting with a fusion-relevant neutron source is essential for our fusion program, for the World Fusion Program, as a successful experimental fusion reactor. And in my opinion, my personal opinion, which is shared by many, not by the policymakers, it's even more urgent. Certainly follows an independent research road. We are the same community, but the skills are different. It's even more urgent. We should know exactly which material we will be using for them, and we don't know now. It's essential to start as soon as possible towards the long life of the fusion program. And I will try now in the next slides to explain how far are we to conceive counting with a 14 MeV neutrons in the near future. And the answer is easy. We are very close, and you will see how. And in fact, this concept of stripping a deuteron and obtaining neutrons, stripping the neutron from a deuteron by impacting on lithium screen and getting neutrons of 14 MeV is something, an idea that is already 14 years old. And it has been a subject of continuous development worldwide for the last 30 years. However, it's very difficult. That's why we're still not there. But why do we need this specifically, this 14 MeV neutron source? Why cannot we live with the neutron source available around? I mean, the reason is one. I mean, the DT reactions have a spectrum which is radically different to the spectrum that we have in fission reactions. In fission reactor, we have a wide spectrum of neutrons energy, and in fusion, we have a monoenergetic neutron at 14.1 MeV. In a fusion power plant, basically for 1 gigawatt, it depends very much on the energy and the power that the power plant will have. But basically, for 1 gigawatt, we will need about 10. We will have about 10 dPAs per year in the equatorial, in the most irradiated regions, in the equator of the. I don't know if you see my mouse. In the equator of the right of the straight part of the tokamak, the TF coils. And in fact, the main problem in structural matters, structural materials, is that there are two reactions on iron with threshold energies, typically above the average energy of fission reactors in particular. The one which transmutes iron into chromium, liberating an alpha particle, which has a threshold energy of 2.9 MeV. There is also another transmutation reaction which goes from iron absorbing a neutron and liberating a proton and transmuting into manganese. So basically, the structural materials which are based on iron, steels, lose their nature. And the alpha particle, which, as you know, is helium, becomes a gas in the lattice of the material. And this is the problem. The accumulation of gas in the material's lattice is making swelling of the steel with the difficulty that noble gases are not solved in metals. That's why we tend to go to reduced activated ferritic martensite steel that possibly you heard about, the RAFM, and for fusion reactors, as a solution to accumulate this alpha particle, this gas, because the structure, the lattice of the reduced activated ferritic martensitic steel, well, the ferritic martensitic steels themselves hold some kind of interstices, some kind of volumes, which this allows the accumulation of the gas. And the swelling, which can be very, very substantial for austenitic steels, leads to rapid embrittlement of materials. In fact, if one compares the fusion materials with fission materials, all the difficulties that the fusion materials are going to be undergoing in a nuclear reactor, if we compare with the fission reactors, we can see that the solicitations are substantially stronger. I mean, we have to deal with very high fluxes. Okay, these fission reactors also, materials in fission reactors also do. But we'll have to be facing cyclic stresses, which in fission reactors we don't have. And in particular, due to Lorentz forces, they can be up to above 100 megapascal. Thermal loads in the divertor above 10 megawatts per square meter, which even can reach 20. And helium and hydrogen generation at the 14 MeV of about 12 atoms per million of helium per dPa, which is enormous. Typically, a fission reactor is yielding 0.3 atoms of helium per dPa, which is substantially lower. And spallation sources we have in Belgium, the construction one. Spallation sources are okay. They are sold sometimes as a solution, but they cannot be because again the spectrum is very wide, and in particular, in what concerns the swelling of the materials is radically different because the generation of helium atoms is above 50 per dPa. And as you know, the fission reactors have a neutron average of below 2 MeV. So this transmutation of iron into chromium doesn't take place, basically. And spallation sources are generated above 20 neutrons per reaction and are pulsed, which is also a problem because we have seen some hysteresis in the materials by kind of self-annealing when they are not irradiated. So the degradation of the materials is very much correlated with the steady state of future fission reactor, and not with a pulsed nature. So in general, just to summarize, understanding the degradation of the physical properties of materials exposed to 14 MeV is a key parameter for the design of future fission reactors. To have a reliable design, and certainly to ensure the facility licensing. We are already learning in Cadarache, in ITER, that the regulatory bodies can be very tough. So this is an essential step. And indeed, we can have data from all kind of sources if you want, because the variables playing a primary role are substantial, are many. Unfortunately, we don't have only one. We have neutrons spectrums, which is a variable that is impacting a lot. Neutrons fluence, temperature, thermomechanical history and microstructure of the material, mechanical loading, lattice kinetics. And you need to say, in ITER, you don't have a problem? No, because in ITER, we will only be having 3 dPa at the end of the machine lifetime. But in a fission power plant, we will have above 10 dPa. About 10 dPa because we will have about 10 dPa per year per gigawatt. We don't still know how demo will be. We talk about 1.5, 1.8, 2. Initially, we talk about 3. Certainly, a power plant will have very likely to try to peer that of a fission reactor, so it should be 3 gigawatt thermal power. So it would be far above 10 times more than what ITER will suffer at the end of its life. So, and this is the situation we have now. I mean, we know very nicely because in fission reactors, we have been able to have experimental fission reactors from the very beginning. So there was no problem to test materials in real conditions. In fusion, we cannot do that. We don't have a fission reactor. ITER will be the first fusion reactor to work in steady conditions. So we know exactly, we know very well, even the simulations have been benchmarked. So we know even by computer tools to anticipate what is going to happen to materials exposed to fission reactors, to fission neutrons. And we also know from data obtained from ion implantation, from spallation sources, from all kind of different sources of neutrons, we also know how can be, let's say, the worst possible scenario of degradation of a material. Our guess is that the fusion reactors will go in the middle, somehow in the middle, but we don't know. We know that it correlates pretty nicely up to 30 GPAs. So this allows to anticipate that reduced activated ferritic magnesitic steels can very nicely work likely for 2 years with no problem, because we know already that they can hold up to 30 dPAs, more or less correlated with what we have seen in fission reactors. But afterwards, we don't know. And certainly, if we want the fission power to be a commercial solution, we need to allow the reactor work for more than 2 years without a major intervention. So today you can be sure that talking of a demo, smaller, faster, simpler, cheaper, but without counting, and they cannot count because it's not yet available. A fission relevant neutron source is like talking of Alice in Wonderland, to be honest. A review of the technological alternatives for a fission relevant neutron source was already done 45 years ago. You have there the proceedings of a conference in the States in the 76, where they already said that they made an exhaustive exploration of what could be the solutions for a fission relevant neutron source, and they concluded that the best option would be lithium deuterium neutron stripping reactions, as has been always afterwards. And they started in a very optimistic way. To be honest, this paper I adore, and every time I have a look at what they say, I remain without words. Certainly in the 70s, 75, 76, they were already saying that having available fission relevant neutron source in 14 MeV neutrons was becoming critical to the development of the planned experimental power reactor that were aiming to be in operation by the late 80s or early 90s in the States at the time. So they were doing things in the right manner. They were trying to understand first the behavior of the materials. But what shocks me most is this little paragraph here highlighted, which at the time they were very optimistic. I don't say that they were, I could say that at the time it was an academic paper, academic project, because they were saying in a very affirmative manner that the technology was basically state of the art in what concerns liquid metal and accelerator field. To achieve a Galois relevant neutron radiation test facility, and that this facility would be made operational as early as 81. So it was said in 76. So that's great. Yes, certainly Alice is there. So what I can say now, we can say now in 2020s, that world accelerators technology was not ready by far in the 70s for a high current accelerator in CW mode. What this means, I will explain later. And neither liquid metal technology was not ready in the 70s for such a massive lithium target. In MIF, we are considering, I will explain what MIF is afterwards. In MIF, we are considering that we will need 10 cubic meters of 20 cubic meters of lithium. So I will explain where we are with this option and all the other parallel options that we have developed since. But what I can tell you is that no magic ideas have appeared since then. I mean, there had been one very beautiful idea from the Russian Federation, from Novosibirsk, from VIMP, Woodkar Institute of Nuclear Physics, that was unconceivable in the 70s, and it's based on magnetic mirrors, which is very appealing, but I think that still we are not there. And basically, there are two mechanisms. Either we utilize accelerators with gaseous targets, with liquid targets, or with solid targets, or we go for plasma-based systems. So regarding using an accelerator and a gaseous target, there was a few years ago a very curious project announced very loudly that they were claiming that within 4 years and 20 million euros, they will be able to provide for DPAs full power year. I have the good pleasure to be one of the reviewers of the paper, and I can tell you they had a difficult time. What they were proposing was a tritium volume at 4 kPa containing 2-liter vessel, and be impacted by a deuteron beam at 300 kilo electron volt. And they were basically cloning something that they were doing for for other applications with a deuteron gas and deuteron beam, which is fine. But having a tritium gas in a volume, I mean, this is something inconceivable. I mean, all the difficulties that we are having in ITER for having 1 gram of tritium during operation, it's enormous. So having a volume of 2 liters containing 4 kilopascal of tritium and being impacted by 300 kiloelectron volt deuteron beam to 10 neutrons, with no reference in their explanation, these 20 millions in the breakdown of any nuclear safety matters. Well, I mean, this would have never been approved not even in a undeveloped country. And in fact, I mean, it's not even considered in the table you will see afterwards. So it's a purely academic paper. Liquid targets. This is has been developed since this concept since the early 80s, and it's basically the idea is to have 2 deuteron accelerators, high current, 125 milliamps, which is for an accelerator is pretty high. But what is a very special feature is that this continuous wave, which means that the duty cycle is 100%. Typically, accelerators work with very low duty cycle, but this accelerator is aiming to work in continuous wave. Then the beam adopts a cross-section of a rectangular and impacts on a lithium screen, which is flowing at 15 meters per second, which is very fast, 15 meters per second, because the power is very high. I mean, it's 10 megawatts power, twice, so 10 megawatts beam power, which has to be evacuated. And okay, this project in the 70s, in the 80s was absolutely impossible to do. Basically the accelerator we didn't know how to do. The idea is to have, well, with this concept, you can see the stripping reaction is a very funny reaction that was theoretically predicted in the 40s by a guy called Server. The paper is also very interesting because it's basically classical mechanics by which he describes the rupture of the nucleus, and he predicted the energy of the power that the neutron that would be depleted from the deuteron would have, depending on the energy of which the energy is playing around. So basically, if the deuteron was impacting, they would predict that 40% of that energy, of that power, would go with the neutron. And this is what we are doing. That's why we have 40 MeV deuterons stripped 40%, give the peak at 15 MeV, and then it drops. So we have deuteron, sorry, we have energies below, but a real peak at 40 MeV, and then it drops the flux. And the idea with this we will have a high flux text module in which we will have 3 different volumes, a very narrow, small one of half a liter that would be enjoying, let's say, 20 dPa per year, that would match that of a demo reactor. If we go for 3 gigawatts or 2.5 gigawatts thermal power, 1 dPa per year in 6-liter volume, and 1 dPa per year in 8 liters. One of the challenges is also the facility to avoid this point that I mentioned before about hysteresis is the availability of the facility that should be above 70%, which is also very challenging. So the efforts to construct this facility started in a very strong manner, very dynamic manner in the early 80s in the US. They tried to demonstrate that the accelerator was feasible. The accelerator, as I was saying, is very challenging because it has to run in unprecedented conditions. But they had just been invented a device in the Russian Federation in the late 60s, early 70s, which is called RFQ, radio frequency quadrupole, that allowed dreaming of these conditions for low betas, for low relativistic betas. It's not a plasma beta, for low speeds, for low energies, like the 10.5 MeV means in an accelerator. If MIF stands for International Fusion Materials Irradiation Facility, and the project that remains nowadays, possibly you heard about it, because it is an S3 project and is possibly going to be constructed this decade. It's called DONES, MIF DONES. DONES stands for Demo-Oriented Neutron Source. As I was saying, it has been included in the S3 program roadmap as an strategic infrastructure for Europe. So in the 80s, as I was mentioning before, the US, they started in a very aggressive manner the development of an accelerator. They were expecting to have 100 milliamps in continuous wave at 35 mega electron volts. These were the conditions of the project at the time, so they would be getting slightly lower yield of neutrons, that's clear. The project was called FMIT, which is basically FMIF, is Fusion Materials Irradiation Test Facility. And this is you have here the schema of the accelerator. They started very strongly, but they faced difficulties. The reality is that at the time, the technology was not ready. And they constructed an RFQ. They were expecting to validate 100 milliamps in CW. Instead of using deuteron, they decided in a clever manner to use H2+. To be honest, this is also something that shocks me. It's true that the beam physics was not properly understood at the time, in particular what concerns the beam halo, which is a phenomenon that appears when you have high currents at low energies, driven by the space charge phenomena because of the repulsion that the particles start to have between them, and some of them are kicked away. And when you have very high current, this beam halo, if you increase the duty cycle, then it starts to make noise, because then the power starts to be substantial. The energy deposited starts to be substantial. So they try to run a 100 milliamps in CW with an H2+ at 2 mega electron volt, which it's very low energy also. And basically they didn't manage. They managed to run for a few minutes and they burned the RFQ in a very rough manner. So basically the project was stopped in the 85. They canceled the project because they saw that the technology was not ready. And the fusion program together with this in the US went to pas perdu, we could say. And in fact, the beam dynamics was insufficient. H2+ was assumed to behave as D+, but it's completely different. And also one of the problems that they faced was the presence of the beam halo was very much induced by the pure gas fraction of the injector. The injectors at the time were very poor quality. They were cathode based, and you can see there the injection of the current in the RFQ being 110 milliamps to reach a proper transmission in the output of the RFQ to 100 milliamps, assuming 10% losses. For that to reach the 110 milliamps, the injected current needed to be 200. Well, the current in the injector needed to be 250 milliamps, which was very dirty. They needed some bending magnet for ion fraction separation to make the distances longer, and these distances in accelerators, in what concerns the beam halo and the space charge phenomena, even 1 meter is something terrible, because the beam expands. So things need to be very, very narrow. So they basically didn't manage. But in the 90s, there was a breakthrough in accelerators that was essential, and it's essential for the high current accelerators, and it's indeed in application today, which was the electrocyclotron resonance accelerators for the injectors. And this allowed to have a gas fraction above 90%. So for example, to reach, as we have in Rocasso, accelerator in Rocasso, to reach 140 milliamps injection in the RFQ, we have an output current from the cathode, let's say, from the source, of 160, 170 milliamps. So the gas is very pure, and then the things can be done very compact, and then the space charge phenomena can be controlled. And in the 1990s, then the US, they are also very active, very proactive. They took rapidly in Los Alamos, in the same laboratory where they had failed with the RFQ for Smith. They had a community expert on these efforts of high current accelerators, and well, they tried, they conceived an RFQ in a very clever manner, could make the tuning of the beam inside the RFQ by a dual cooling for the inductive and the capacitive part. And they using the ECR concept with an 8-meter long 300 megahertz, 250 megahertz RFQ. They managed to run 100 milliamps. They didn't use any more H2. They use H+, so protons, at 6.7 mega electron volts. They ran for 8 hours in total, for a few hours in continuous manner. They had some problems with the DC heat dissipation, but basically the concept was demonstrated to be successful. So we could accelerate to 5, 6, 7 MeV beams at high current without major difficulties from this time onwards. They tried to convince the fission community to go for FMIT or for a concept of FMIF, but they didn't manage to convince people. And so they decided to try and understand the beam halo, to use the device and try to understand the beam halo, which was still a mystery at the time. There were some models, but there were no way to measure. And they devised this project in the early 2000s with 52 quadrupoles set afterward the RFQ, and changing the signs and changing the fields, trying to anticipate what would happen with the beam halo. And they managed to match the simulations and the calculations with the observations. And this is what I was saying before. Then they tried to convince the community of fusion and they even presented in a conference of an ICFRM conference in fusion reactor materials, to convince the community of fusion materials to go for IFMIF in a very kind of mild manner, where you're making use of the accelerator, the RFQ, and the injector that was already operational. Okay, but they didn't convince the community. At that time, the community was focused on approving ITER, and I mean, it was not time to think of IMIF. And I would possibly have had the same approach if I had been in the policymakers. Anyhow, there was something that was very happened also in the early 2000s at the time, which was the development of the superconducting cavities for low beta beams, for slow beams, and light hadrons in particular. This kind of superconducting cavities have been used for heavy hadrons, but for light hadrons was not still performant. And they managed to demonstrate that it was feasible, and this was also a breakthrough in accelerator technologies, because well, you have here what does it mean. You have in the right here the quarter wave resonator that can work at very low betas, but this beta is the relativistic beta. It's the speed, the ratio of the speed by the speed of light. A half resonator that can work at very low frequencies in a very nice manner. And indeed, the DTL, the drift type LINAC, that was typically used for LINACs to accelerate beams up to the superconducting or the cavities or the radio frequency cavities, had difficulties because of the geometry. Had difficulties to house high currents. In particular, for 100 milliamps would have been absolutely impossible, I would say, because of the beam losses. I mean, the drift turbines, I guess that you know how they are kind of narrow tubes, which are kind of Faraday caps, and then an electric field, which go in their length go with the the space that the beam is going to travel at a given energy, and then there is an electric field that is changing at the distance of these tubes, in the gaps of these tubes. So everything has to be very well matched and very well designed. But if you have very high currents, again, we have these very high duty cycles. If you have a low duty cycle, you can live with. But if you want a high duty cycle, 100, like the continuous wave, and high currents, then it's basically practically impossible because the heat dissipation is overwhelming. So in '94, they started with IFMIF beta, with IFMIF, and in 2007, upon the 2006, 2007, upon the ITER agreement approval, the IFMIF beta phase started. IFMIF, we already know what it means, and the beta phase, which still runs in the broader approach agreement, which is a collaboration between Japan, bilateral collaboration between Japan and Europe, and Euratom, framed in Europe by Fission for Energy. It's a department of Fission for Energy. And the beta is engineering, it stands for engineering validation and engineering design activities. And the scope was to produce, the mandate was to produce an integrated engineering design of IFMIF that we did, and the data necessary for future decisions on the construction, operation, and exploitation, and decommissioning of IFMIF. And what is relevant also is to validate continuous and stable operation of each IFMIF subsystem. And with this same, full-scale prototypes were constructed. Well, sorry, the countries that are joining IFMIF beta under the umbrella of Fission for Energy are Spain, led by CEA, sorry, France, led by CEA, Spain, led by CIEMAT, Italy, with the contribution of ENEA and INFN. Belgium is also a participant. In particular, they were very, very active in the design of the facility, in the design activities. This is with the lab SCK-CEN. Switzerland under EPFL, and German with the Karlsruhe Institute of Technology. And in Japan, under the umbrella of QST, which was formerly JEA, the main Japanese universities. So in the IFMIF beta, we have constructed various prototypes. One which is still to be fully validated, the only one missing, is called LIPAC. It stands for Linear IFMIF Particle Accelerator. It aims to have 120 milliamps in CW at 9 MeV. In IFMIF, as you know, we will need 40 MeV. But this space charge phenomena is particularly relevant at low energies. As soon as you reach higher energies, relativistic effects cancel the repulsion of in a very funny way, the repulsion of the particles because of being together goes cancelled with the Ampere law, if you want, by the particles by attracting together. If you have currents in the same direction, two lines in the same direction with flowing current in the same direction, putting in parallel. So the spatial phenomena cancels a relativistic speed. So if we validate with the first superconductive cavity in IFMIF, in the accelerator of IFMIF, we will need 4 superconducting cryo modules. In LIPAC, we will have 1 superconducting cryo module, but if we validate at 9 MeV, which is the first stage, we are certain that it will go up to 40 MeV. Obtaining these values today is not a dream. We can see here that we have various projects in the world. In particular, MIRA is not so far from what IFMIF is going to reach. MIRA is aiming to have 2.5 megawatts of beam power. The European Spallation Source, it's 5 megawatts, I think, that they have integrated recently. Chinese, with their ADS, it's accelerator driven systems, that they are very strong trying to develop this technology. They are aiming to have 15 MeV this decade. And there are also in the world ideas for 100 megawatts beam power. We are not only the accelerator, we have also worked a lot on the lithium target, on the lithium technologies facilities. There was a one-to-one scale, basically one-to-one scale lithium loop fabricated in Japan, in Oarai, near Mito, near 100 kilometers from Tokyo, in the south of Tokyo. In Brasimone, in Enea, in the north of Italy, there has been a facility also that you have there on the left that to address corrosion of the reduced activated ferritic magnetic steels exposed to flowing lithium. And there have also been some development of remote handling for the lithium target that will have to be removed on a regular basis, possibly one per year. And the outcome of this validation activity has been very successful. One of the main challenges that the lithium facility needs to face, that was conceived as a dream and impossible to meet, is to have a stable lithium flux to ensure that the beam by no means would touch the backplate, because 1 milliseconds of 40 megawatts touching steel, you can imagine what happens. It's very easy to calculate. So you need the lithium screen evacuating the beam power in a continuous manner without failure. And the specifications is that the fluctuations of this lithium screen, which is 25 millimeters thick, is to be plus minus 1 millimeter with no variations. And it has been demonstrated. It was for 1 month, 25 days running in a steady state manner. And you can see in this Excel file the overlapping of all the points. You have here the measurements that were performed in the elapsed time of hours, and you see how perfect. I mean, this is the stable area. I mean, this is the edges. So this is not valid, but even here. But here you can see that all the points are overlapped. One of the concerns was also the vaporization of lithium. There were many experiments that have been done around. It's in the 70s, in the US, in Russia, in Japan, and they were not convincing, and we didn't manage to obtain a proper result. But in this exercise that we have done underneath MIFE Beta, they have managed to make a brilliant exercise. I recommend you, if you like liquid metals, to have a look at this paper, which is of Kanemura-san, because it's a wonderful paper. I wrote a little paper with him, and mine is much more humble, together with him, somehow to anticipate what he was going to get. But his paper is really a masterpiece. And he demonstrated that indeed, I mean, there was no problem of vaporization. He anticipated with his model what the vaporization would be, and he measured it. And in Lifusis, this facility in Brasimone, a small lithium loop in Brasimone, they were measuring the corrosion of reduced activated ferritic martensitic steel, which is going to be the material of the backplate, exposed to a flowing lithium of 15 meters per second. What happens? In particular, the reduced activated ferritic martensitic steel. The steels are very sensitive to the presence of nitrogen. Nitrogen makes some depletion of the chromium, and then the steel stops being steel because the chromium disappears, and then you have all sorts of different problems. And well, it was demonstrated that the corrosion rate expected of 1 micrometer per year of operation can be met, but with a very tough control of nitrogen, which is not straightforward. We were specifying 10 ppm of nitrogen, and it's basically impossible. I mean, 30 ppm seems that was feasible by some technology developed, combination of technology developed in Japan and in Brasimone. And another major point that was always under discussion, and we also managed to overcome, was what would happen with the lithium absorbing the 10 megawatts beam power. And okay, you have here, I mean, we have a radius of 250 millimeters in the back plate. And this 250 millimeter with a 50 meters per second make centrifugal pressure that goes on the order of kilopascal. And if you see which is the vapor pressure, how the vapor pressure, the boiling temperature goes with the vapor, with the pressure of the material, you see that it goes in a very drastic manner to values above 100. So the lithium, which melts at, is going to be flowing at 250 K, it melts at 200. I mean, it has in a permanent manner at least 40 K of temperature margin. And okay, we are moving into if MIF dones, if MIF beta continues. but the scope of IMIF beta didn't include the mandate, didn't include the construction of IMIF. But the success of IMIF beta has allowed to keep on pushing, and the need of a fission relevant neutron source has allowed to dream on having IMIF Dones, which is it's a project that is started in a very humble manner, in a very timid manner in the south of Spain. It has been approved to be hosted in Spain, and is sponsored by Croatia and by Spain jointly, and the European Commission is also supporting. However, we have the roadmap. I have a roadmap here. Yes, we have a roadmap ahead, and we rely still on a hold point, which is on the superation of a hold point, which is the success of LIPAC, to show that we can really run, that we have not seen up to now, that we can run at 125 milliamps in CW mode through the RFQ and through the superconducting cavities. This we still don't know. We hope that we will manage to do. It will suppose a breakthrough, a dramatic breakthrough in accelerators technology that will have make a lot of noise, because this will allow to have all sorts of applications, not only for fusion. But I think that things, to be honest, I trust that things are ready to make such a breakthrough. The RFQ is an improvement of the same of LEDA. It's slightly longer, but it has the same concept of the dual cooling, the tuning of the beam in a direct manner to minimize the heat dissipation and to minimize the problem. So as soon as you show that there is a heat dissipation somewhere, so that the RFQ that has very tight tolerances, the beam starts to detune, and then this you identify because you have higher losses. Then you activate the cooling such to cool down wherever it is hot, or to warm wherever it is cool, so that you can allow the tuning of the beam in a direct manner with this dual cooling power that worked in LEDA, so will work in an upgraded manner in LIPAC. We already know that it works with low duty cycle, and the campaign for high duty cycle is going to start this year. So the roadmap is like this. We hope to start the site preparation, to sign the site preparation contract in 2024, and the buildings immediately after, and to have the buildings ready by 2028, and in parallel start the main contract. So to have the operation in 2032, so timely for having some material results to allow the design of demo as soon as we have the deuterium reactions. And this is some slides to show that the activities under the Eurofusion program are continuing in what concerns the development of tasks related with IMIF Dones. In particular, one of the things that I was mentioning before, the challenges of the accelerator is the availability. It has to have above 70%. There has been a very exhaustive RAMI done, and the accelerator is one of the challenges. And the radio frequency cavities are one of the challenges, in particular the power supplies. So the new concept of solid, well, not based on power supplies, not based on traditional technologies, but modern technologies, which allows having modular radio frequency power supplies is in place, so that this would allow to enhance substantially the availabilities. And one of the developments is the high flux test module related. It is STUM, which is the initial high flux test model that is going to be installed such to allow the characterization of the beam. Related with solid rotating targets, this I finished with the liquid ones. The solid rotating targets, there are various projects around the world that have been conceived. Basically, they are based on accelerators or which are either deuterium or tritium even, which this is certainly an academic project, in a rotatable target, which can be deuterium doped somehow or tritium doped. So what you obtain is in the target by the action of the beam and the absorbed deuterium or tritium, you obtain the neutron reaction and the neutron flux. There was an idea started in this conference in the 76 and a project that was very successful with an injector. You don't need very high energies. It's about 300, 400 kilo electron volts, but neither very high current because you cannot get them in injectors. So it's a very simple project. However, the main difficulties are in the rotational target. I mean, the rotational target. I mean, the beam dissipations are enormous. In adiabatic conditions, for example, in this project with that had a yield, maximum yield of 10 to the 13, at 14 MeV, they had 200 megawatt per cubic centimeter of beam power. In adiabatic conditions, this means 10 to the 8 Kelvin per second of increase of delta T. There has been a few projects around the world. This is a table summarizing all of them. You can retrieve them from this paper. And basically, the peak keeps on being the same. We don't manage to get even with nowadays technologies above 10 to the 14 neutral yields, and we need 10 to the 18. So it's for orders of magnitude. And clearly, then the DPAs that you can obtain with these kind of projects are insufficient to properly qualify materials that we know that are going to be exposed to 10, 20 DPAs per year. And there was an interesting project that was competing with IFMIF at the earlier last decade, which is called FAFNIR, what is now abandoned, which was aiming to have a 30 milliamp CW current and impacting on a rotatable target that in an initial phase they were expecting to reach 200 kilowatt, which was double of what is feasible. I don't really know if they have managed to anywhere to have a rotatable target allowing a beam of 200 kilowatts. And they were aiming to have 1.2 megawatts. So, I mean, it was really science fiction. Also, the accelerator at 30 milliamps in CW with a DTL concept was not feasible. Okay, this is fine because they would have been also passed on to the superconducting approach as it did in IFMIF beta. But anyhow, I mean, it was not feasible. But what shocked me more when I learned a bit more of the project is that the cross sections of the reaction that they were expecting to have, the carbon deuteron neutron at 40 MeV, were not really understood. So, I mean, if you don't know what the cross section is, then you don't really know what is going to be the yield. So, I mean, the project was weak, so it was never approved. And we are approaching the end. Plasma-based systems. There has been from the States a project, component test facilities called that was. I mean, I don't know what adjective to find. I mean, in Europe, I don't think that it would have never been even conceived, something like this. In the US, they are a bit more aggressive sometimes. And basically what they were aiming is to have a tokamak to test materials. Fine. Let's first learn how to make a tokamak, and then we can think of making a tokamak to learn materials and not starting to construct a house from the roof. I mean, the problems that this project would face would need an IFMIF facility to be designed. I mean, to be overcome, because they would be facing the same material problems that we would be facing in ITER. So no more words on this. But what is interesting is a project that has been conceived as I mentioned at the beginning, in Butker Institute in BIMP, Novosibirsk, which is based on mirrors, on magnetic mirrors. And well, I mean, it's a clever idea which allows to conceive fission reactions for a reactor as such. For a power plant doesn't work because the length between mirrors would be of a few kilometers with the present concept. But to be developed to obtain neutrons for material testing is possibly something that can be materialized in the next decade. They basically have they have two systems based on fast ions injecting for MBI, which are basically the same as ITER, and they have the same difficulties as ITER is facing for the MBI. So the technologies that develop in ITER would serve also for them. and warm ions, which are operating basically as an ideal gas, and that provides stability to the plasma. And the concept is a bit complex. They have kind of limiters that make some vortex, and they basically match the theoretical approach with experimentation. They have been operating for a few decades already, and they can even work with high betas. This beta is the plasma beta, so it's the ratio between magnetic and gas pressure. And okay, you see here where the testing areas could be. In these peaks you have here is where basically the high flux of neutrons it takes place. So also this allows a very easy maintenance, because basically in the core of the device the radiation is very low, and you would also need to focus on the maintenance on the high flux areas, which is where you would be testing the materials. So let's hope that, because this allows a high volume, so let's hope that this materialize, and so the next decade we can count with MIF and these kind of concepts to test material, because it's something that we really need. I have here a summary of the assets and drawbacks, and as I stressed that it's a necessary position to become a reality and support the first results of MIF donors. And this is a table that you can retrieve in this paper, where I make a summary of the pros and cons and the main features of the different concepts. This visual here is an interesting one. To be honest, I don't know if they are still making noise or not. It was a kind of MIF project that the Chinese, as you know, that they like to copy things, were aiming to do. They didn't want to take risks, and they were aiming to have just 10 milliamps, because they had already managed to have in some Chinese lab 10 milliamps in CW deuteron beams. So voilà, to convince their policymakers, they just went to them to 10 milliamps, which would have not been so much interesting, to be honest, at least for them, because with 10 milliamps you obtain what they want, 2 dBs per year. But okay, I mean, it was an interesting project. They made a lot of noise, and to be honest, as I say, I don't know anymore where they are. So just to conclude, phenomenal materials exposed to fission neutrons can be anticipated through simulations, and this is very good because they can even avoid making sometimes experiments thanks to the benchmarking of their experiments throughout years with no difficulties with experimental reactors. But in fusion, unfortunately, we don't have such gift from God. We don't have fusion reactors available. The availability of 14 MeV neutrons to characterize and qualify structural materials is indispensable. We know that the RFAM can hold up to 2 years of demo, not more than that. But for a commercial power reactor, we would need to convince either private investors or the electrical companies or the governments. You cannot just make a long shutdown every 2 years. You want to be financially interesting. So we need material that can hold more than 2 years. Also, we need a fusion relevant neutron source to test materials. There are materials that are conceived beyond reduced activated ferritic martensitic steels, which I think that they are at the limit, which are carbon silicium composites, vanadium alloys, and other sophisticated materials. But we are not yet there, but I hope that we will. And there is also, we haven't gone into it, there is an extensive and very successful research program for ancillary equipment like materials like ceramics, seals, electronics, which is very successful with a lot of wide community, but we have not addressed it. What is really critical for the fusion program is a 14 MeV neutron, because this is not available. For testing this kind of equipment, we are not exposed to 14 MeV. The available radiation sources are perfectly suitable. And today, the needed flux can only be reached through the stripping reactions of lithium with deuterium. And this project, if MIF dones, is basically warming up to start playing in the fusion platform. So let's hope that everything goes in as we hope, and the next decade we will have fusion 14 MeV neutrons available. So I will also, just to finish, would like to thank Angel Ibarra from CIMAT and Vadim Prikotko from BIP to help me with some material for the talk for the work on immediate donors and GDT. To Jeff for organizing these nice talks, and to all of you for your interest. And if, I mean, for the sake of intellectual property, we cannot make official the distribution of these two papers and whatever other paper I make reference. But I would be very happy if you are interested to have them to send to you if you send me your email address. So thanks to all of you.
Thank you very much, Juan, for very interesting talk. I learned a lot of things, which I mean, I did here for the first time here. I mean, the overview of the different sources and the GDT in Novosibirsk. I mean, they look, I mean, interesting things, which it's the first time I hear about it. Of course, I'm not in the field, so it was very useful for me. I hope it was also the same for the people who participated in this webinar. And now we have time for questions. And I mean, I really would wish several questions from the people which are there. And I would ask, I mean, if you could raise your hands. On the Macintosh, you have a little symbol reactions. If you click on it, you can raise the hand. I think on the PC, you have to go in the participants overview and then raise your hand there. In any case, please do, or otherwise, I mean, just tell that you want to do. I see already one hand raised, which is by Vladimir. Vladimir, please.
Thank you. Are you hear me?
Yes, yes.
Thank you for interesting presentation. It's really a great amount of work to do with materials. My question is more not about the source, but about the materials. So as I understand now, existing materials, even with vanadium and the Eurofer, they withstand, first of all, for maximum 1 year for continuous source of neutrons. What about it's not commercially compatible? So are the candidate materials for which could withstand a longer time? And the first question, and the second one concerning the pulsed regime. For example, for inertial fusion, we are more interested in the same power, but in the pulsed neutron deposition, say with periodicity of 10 pulses per second and so on. Would it change the existing materials? And concerning the smaller tokamaks, like spark, would the same conditional materials, or it will be harder to withstand? Mm-hmm. So many questions. Sorry for that.
It's fine, it's fine. I mean, regarding the first question, which was materials, I mean, for them, I don't think that there is a big deal. I mean, we need to demonstrate that what is the limit of the materials, of the structural materials in demo, and to demonstrate with 14 MeV neutron, because at the end of the day, what we have now are speculations, and the regulatory bodies, I'm certain that they will be asking for real data that is reliable. In particular, for example, there is a program sponsored by the IAEA, which is aiming to have standards for the small specimens that we would be using in MIF donors. Because I trust that if you go in 20 years' time with data from small specimens to the regulatory body and saying that you are convinced that what the small specimens are yielding is correct, they are going to challenge this data. So we need the standards, so to be sound in our approach. And this is being driven by the IAEA for the time being. So we hope that we will have timely at the time of IMIF beta, of IMIF donors startup, some, if not already standardized specimens, very close to be standardized. And the fact is, in my opinion, the viability of a commercial fusion power plant cannot be if you need to replace the first wall every 2 years. I mean, you have to make a shutdown every 2 years. Of course, you wouldn't have to replace all the walls. The radiation map inside along the perimeter, the toroidal perimeter of the vacuum vessel, or the shape, the D shape is changes strongly depending on the position. But in the hottest areas, certainly you will be having around 10 GPAs per gigawatt per year. So, and the reduced activity for the Martin Sicken steel will not hold. Will not hold for years, for example. So you will need have to shut down. Vanadium and carbon silicium. I hope that, I mean, the carbon silicium, if I understand right, is basically not affected by the 14 MeV neutrons, so it would be great too. But I mean, the materials problems is substantial for fission. We really need to strong development there before we can reach a commercial power plant. For demo, I don't think that it would be a major issue, because demo at the end of the day would become still, to my perception, I mean, anticipating what is going to happen 40, 50 years from now, 30 years from now, is going to become an experimental somehow of a prototype of a power plant. So if you are not commercially appealing, it's not the end of the day. But indeed, for the next step, which we hope that will happen in this century, of commercial power plants available, we still need a lot of materials development ahead. Regarding the second question, which was, can you recall me, please?
Pulse power, pulse to energy deposition.
Yes, right, yes. Well, of course, I mean, if materials-wise, we have seen that there is some hysteresis. There is some kind of annealing of the materials, but everything is, I mean, it's not properly understood because of the lack of the 14 MeV neutrons. But certainly, if you have a duty cycle, you have less DPAs as such. You have less neutrons, so it would go in the right direction to enhance the material life. But the power, it's also is somehow affected. I don't know in which way, but the power in the grid, or the energy you want in the grid with a steady-state manner reactor or in a pulse reactor is different. So it will also have an impact of the yield of the power plant. But to be honest, I'm not involved so strongly in the concepts of new power plants as to understand, the future power plants as to understand exactly what is the impact. But certainly, yes, I mean, if you are not in a steady state, you have to somehow of pulse manner, you have the amount of neutrons is correlated with the pulses.
Well, number of neutrons is the same. It's just they go in time unequally. So I understand that mechanically it's more challenging, but in terms of DPA, probably it's the same.
But the fluence, no. I mean, if you have 10 pulses per minute, or you have a steady state way of reactions, you have different number of neutrons. Fluence, at least.
No,
of course,
in average number of average power is the same.
Okay.
It's just the pulse power. So it's distributed unequally in 1 second instead of continuous. I have 10 spikes.
Okay. Well, I don't know exactly the details, so I cannot really answer. But certainly, I mean, let's say that with the materials there is an hysteresis which is not fully understood. It was learned also for fission reactors a bit late in the 80s, if I remember right. I mean, this is explained in the paper of the fission, the one that was written with Anton Muslan and Murowasan. But yes, indeed, I mean, the degradation is correlated with the neutrons, with the amount of neutrons, so with the DPAs.
And if we reduce the size of the surface, I have the same power again, but I reduce the surface.
Yeah,
compacted tokamak or something like that. Very appealing.
In particular, the divertor is going to, I don't know what.
And divertor, it's the same problem.
The divertor, Alberto, I was talking to him the other day with Alberto Duarte, I gave to you a talk, and he was explaining to me that, I mean, the power densities that they were having in the divertor with with this smaller tokamaks was a factor 3 or 4 higher than what we were facing in ITER. And in ITER, we are at the limit of what we can do. We have these experiments in West and in Cadarache, in Torre Supra, and in other places to try and understand what is happening with the divertor exposed to power densities above 10, 20 megawatts per square meter. And these people are considering to have 3 times, 4 times more. So it's, I mean, I hope that, I mean, I'm very honest also. I hope that all these efforts, I think that all these efforts are good. And I hope, because the difficulties are enormous. And I hope that everybody succeeds. I really hope so. I also think that ITER is doing what we need to do. But all these other projects, I'm very happy that they exist. I'm very supportive to all of them. Emotionally supportive. I cannot do anything else. But indeed, if they ask me something, sometimes has occurred, I am very helpful.
Okay, Vladimir, is it answering your questions?
Thank you.
More or less.
I must see the problems.
We can discussion for hours, I think. Subject. Other further questions? In fact, Juan, I have a question to you. So we have now the IFMI development, which in fact give you a small volume but very high flux. And then there is the GTT, I mean, development in Novosibirsk, which could allow you to have larger volumes. That is what I understood, correct?
Yes.
So do you see a possible combination of the two projects in the future, or how, I mean, because both of them look appealing to me. So how would you see the future of, I mean, having larger volumes?
I mean, the GDT still needs some results of it, if I may, because they need to develop the MBIs in a very drastic manner. They're not doing it. So they rely on the developments of ITER for the successful operation of the MBIs. Mm-hmm. If they manage in ITER to do it, and I hope that of course they will do it, then this can make a step forward, this project. So that's why I say that next decade is likely that they can try to make further noise. They have some collaboration with the US. There's something, you know, in Russia, all these projects have a lot of financial difficulties, and they seem to be having some financial support and some collaboration with the US. Mm-hmm. Which is giving them, making them fly.
Mm-hmm. Then a question which follows on this. In fact, so would it then not be better to wait until the GTT people are ready? Then you have at once, I suppose that the beam developments, I mean, in Padua go very well, which I think they will, I hope at least. And then, I mean, then we would have a large volume with another system. So would we then still build an IFMIF or not? I mean, how do you see the
Well, as I said at the beginning, I think that we need all possible efforts. If MIF, the cost of MIF is not going to be overwhelming as the cost of ITER is not going to exponentially grow. Because we know the technology and we know what has to be done, and basically full-scale prototype has already been constructed, so the cost can be pretty reliable. The only difficulties might be in the facility because of the sealing of some of the hot cells and all these things. But I mean, okay, that's basically commercial technology. Okay. So and also for the design of demo, we really need to understand which are the material properties exposed to 14 eV of the main structural materials, because we don't really know. We have some speculations, but we don't have means of testing really exposed to 14 eV to the DPAs that we will need. So I'm pretty sure that the regulatory bodies are going to be asking for this. Otherwise, I mean, you just go with yes, based on this data here and based on this data here, with 0.01 dPA, here we reach 1 dPA, then we manage to extrapolate to what's going to happen to 20 dPA. No. So I think that if MIF is really necessary for the design of demo. Okay. With standard specimens, I hope that the IAEA will succeed on this. They have organized they call CPA, I think, or something like this. Well, activity, international activity, sponsored by them and financed by them, which is has called attention, and they are making a very good work. So they are aiming to have this standards for the specimens that we are planning to have in IFMIF. So it's very good.
Okay.
And of course, I mean, we will need in the middle term future, if we consider near term future ITER, middle term future demo. In the middle term future, we will need component test facilities and gas dynamic trap and possibly a full IFMIF, such to be ready for the commercial reactor.
Okay. Okay. This explains. Thank you very much. Then there's a question also by Alberto Fernandez. Alberto, please.
Yes, good evening. I hope you are hearing me well. I have a very little voice today, so I will not be talking too much, which is a good thing for you guys. But first of all, thank you very much, Juan, for the presentation. I learned quite a lot of new things, which is always nice to hear and to follow your talk. So thank you very much. Thank you also for mentioning the MIRA project here in Belgium that we also hope could bring some very humble contribution to the study of fusion materials in the near future. I had a question more from a policy side, if I may. The deadlines that you are mentioning for getting the relevant data to build demo and the following designs, if I understood it correctly, was around 2040. We are today in 2021. So what can we do in the meantime to cross what I could call a valley of death when it comes to technology, where basically you have too long time between the fruits of the investment and the investments that are going on? And do you see also a room for material testing reactors, for fission-based one, just to start kicking the studies on fusion materials? I understand that the 14 MeV cannot be the 14 MeV cannot be tested because you don't have 14 MeV neutrons. But at the same time, it could already contribute to have a kind of a roadmap when it comes to developing materials and also to identifying the most promising candidates that you need to test in donors, because the capacity in donors or in IFMIF, because the volume are rather small, so you will have to be very selective when it comes to those testing. So my question was more as a policy guy than a science guy. What do we do now between now and 2040 to make sure that we can keep the financing ongoing on fusion research, at least in Europe? Thank you, Juan.
Yeah, hola Alberto, it's always a pleasure to see you. Yeah, ITER, we really need to be successful in ITER, and we are starting to have some. We're starting the assembly, and then let's say that the noise of the difficulties is very high, very loud if there are some mistakes. So we are to hope, everyone needs to hope that there is no big problems faced in ITER and that the assembly of ITER becomes very smooth. As I was saying, now we are on the screen, and whatever minor difficulty might be facing with the tighter schedule that we have ahead may generate a lot of noise. We are, as you possibly are aware, we are making a new baseline for the schedule of the first plasma. We already know that it will not be met in December 25. We will not be met we were expecting in November 26, but we don't know. Okay, to be seen if we go beyond 27 in Europe, is going to make a lot of noise, very bad noise. So it's going to have an impact on the ensuing 7 years financing. I was always expecting and was optimistic that in MIRA we would manage to have the fusion testing materials that we were devising. I don't know where we are with this, but I hope that this has not been abandoned. It's very important, as you know, also in ITER. I mean, ITER is the farthest now, so it's light. We really need success in ITER, and as you know, there is a threshold in 2037. The license was given for 25 years, and it started in 2012. Sorry, in 2012, and in 2037 it's finished. So you need a public inquiry again if you want to continue. If you don't have the fission reactions before 2035, as there are the TT reactions are scheduled 2035. So whatever delay that we face in ITER is squeezing the plasma campaign, which is possibly not in a realistic manner. So what I would say, what can we do is really to support ITER the best we can, because if we fail or we make a bad step in ITER, it's can have enormous repercussions in the fission program.
Thank you, Juan. What I can say, if Jeff allow me just a follow-up remark, is that we are continuing within MIRA to develop the fusion testing facility. Obviously, it will not as pure and as in terms of neutron energy than IFMIF and IFMIF donors. But they are still pursuing the dream to have a kind of a material testing facility that could contribute to kickstart the work on fusion materials, because
That would be great.
It is very difficult to wait until then. And I can talk from more, like I say, from a policy point of view. It's difficult to wait so long for results. So I think there is some collaborative work to be done, and just to confirm that from the Belgium side, we are now looking into participating into the IFMIF donors consortium and see how we can also contribute with with our knowledge around accelerators and around the small samples techniques to that project. I think it's as you rightly pointed out, is fundamental to make fusion electricity production a reality. But thank you. I think it's important that we keep on that. But the only thing that would miss from a European perspective, if I may be a bit critical, you know my style, so I can, and it's a bit late, so I can be a bit critical, is that we are maybe missing a fusion roadmap materials. What are the steps? Saying that we need to build something within 20 years from now is certainly something we have to do, but knowing all the steps, because not all the materials within a fusion reactor will be exposed to 14 MeV. You will have a wealth of energies, of neutron energies, also going through the machine, and the regulators may also have different point of views on how materials that are not plasma facing components or close to the plasma chamber should react in normal operation. So I think it would be interesting there to have a kind of to join our forces also with the regulators, because it's something that we need to point out. There is no fusion safety regulatory framework as we speak. You have ideas about how it could be, but it's still in development. And I think those two elements are mission critical to deliver electricity by 2050 using fusion energy. Juan, thank you very much once again. And sorry for my voice, but the weather is killing me. Sorry.
No, I can tell you that whatever is in my hands to support joining forces and collaborate, I will certainly support it.
Thank you, Alberto, for the question. No problems with the voice. We fully understand it. Thank you, Juan, for all the answers and the very interesting talk. Really a wealth of information. Very pleased with myself. I think we have had a lot of questions at the moment, and were very well replied. Long questions, interesting questions. We could still go on, I think, for a few hours, pretty sure. But of course, the time is also going, and the food is waiting in some families, I'm pretty sure. So we must now, I think, stop the presentation. I thank once again Juan for this preparation, for the time we invested in this and his very busy schedule. And thank everybody who was present here and participated in the meeting, and hope that you all learned a lot of things. So next week we will have the talk by Vladimir Tikhonchuk on the inertial fusion developments in the world, and also Vladimir will include the recent gain one shots which have been obtained in, I think, the States. And so it will be also a very interesting talk, complementary to the 4 other ones. Thank you all very much. I wish you all a good evening and hope to see you back next week. Goodbye.
Bye, everybody.
Goodbye.
Bye.
Bye-bye.
Bye.